If you're new to the room, welcome to the S4 Stage 2 Technical Deep Dives track. The next speakers are Rich Corrigan, the lead engineer for the California Energy Systems for the 21st Century, and Adam Crain, the founder and CEO of Automatak. They will be presenting Secure SCADA Protocol for the 21st Century. Let's please welcome Rich and Adam.
So this is something that our lawyers have us put up, basically saying that, this is research that was funded by the ratepayers of California, and so it shouldn't be disclosed, but this has been vetted, so this is all approved to be shared publicly. So California Energy Systems for the 21st Century, it's supported by our California Public Utility Commission. It was approved to use ratepayer funding for this research, and it's focused on ICS cybersecurity to protect the grid from a worst-case cybersecurity attack. So it's a collaborative research and development effort between San Diego Gas and Electric, Pacific Gas and Electric, and Southern California Edison. We work with the Department of Energy National Labs, led by Lawrence Livermore. We also engage industry like Automatak, universities like Georgia Tech Research Institute, as well as other national labs like Idaho National Labs. So how did we get here? So we as a utility, we were asking our suppliers, like, why aren't you building things like DNP3 SA into your products? And they said, well, that solves one protocol, but our products support multiple protocols. And so they want basically TLS for SCADA. But TLS doesn't really apply to SCADA because it's too heavy, it requires too much processing, and it doesn't work over serial. So we took a look at what was out there, and we obviously took a look at DNP3 SA. There was also a legacy protocol, which was the SSCP, which really goes back to AGA 12, and it was called SSPP, but it was basically a symmetrical security protocol using pre-shared keys. There was no ability to do key management or rollover. And so, and we also found that a lot of the vendors are kind of frustrated, and so they've all been implementing their own proprietary SCADA protocol schemes. So here, I'll let, this is where our requirements take over. I'll let Adam take over from here.
Okay, thanks, Rich. So the first thing that we did, I guess, starting back in, was it March of this year, coming up with a list of requirements for the protocol. And a lot of these things aren't stuff that's going to surprise anyone, right? It's got to be able to provide a strong authentication. It has to protect from things like man-in-the-middle attacks. It has to protect from replay attacks, all those sorts of standard things that you see in every cryptographic protocol. But there are a number of ways where the requirements differed pretty strongly from capabilities provided by things like TLS. The legacy schemes, well, it's not quite fair to call DNP3 SA legacy, but some of the protocols that are already in the industry, one big way that it differs is that we wanted our basis to be on public key cryptography to ease the burden of key management that we can never fully get away from anyway. So all the schemes where you only had support for pre-shared symmetric schemes, those were, couldn't use those out of the gate. But at the same time, we wanted lower overhead, and public key cryptography and lower overhead don't always go hand in hand. So we had to look for sort of more state-of-the-art solutions using things like elliptic curves. Initially, we wanted the implementation to be an authentication-only protocol. We see that as being where most of the user base will want the protocol to operate. We see this as something that would operate alongside things like network security monitoring. We don't want to have to pass private keys all over the infrastructure just so NSM can look into the packets. But we do want to provide the option later down the road to be able to add encryption for applications where it makes sense. We're hoping by, I think, the end of this month, early next month, to be testing bump-in-the-wire implementations. And we wanted that to be possible for at least the remote outstation side of systems where you would have scalability issues with changing everything out at once, or you wanted to be able to kind of retrofit things in stages. But it's interesting that we aren't actually providing a bump-in-the-wire solution that works for master stations. But for those systems, it's more amenable to changing out the software all at once versus having to do it incrementally. And I think the biggest thing was that the requirement that this has to work over a multitude of transport layers. So it had to work over serial NIP, UDP, any kind of stream or packet-oriented transport. Hey, do we have two requirement slides? Oh, there we go. Or skipped the first one, Ross. I'll let you take a peek of this, the first slide. I think it accidentally got skipped. But one of the key features there at the bottom, and I've mentioned most of these already, is that the protocol also needed to provide one feature that TLS doesn't, and that's a TTL on messages. So in a lot of timing critical environments, you might not want an attacker to be able to hold back a series of packets and then replay them in rapid succession. And that's a feature that we actually borrowed from AGA 12 and 1711. So, at this point in the project, we have, it's about a 40-page protocol specification. It's been seen by all the project members, a number of vendors, and we're really trying to work hard to make this an open project, and it's kind of starting to go through those gates with our project partners and with legal. But I'm hoping that...
Trying to get lawyers from 3 different utilities to agree is a challenge.
So I'm hoping in the not-so-distant future, that's where the protocol specification will be. And in that same sort of GitHub organization, SSP-21, we'll also have a repository called SSP-21 CPP, which stands for C++, where reference implementation of the specification will also live. Getting some clapping there already. Great. So I'm not going to be able to cover all the technical details of the protocol in this session, because some parts are not so boring and not so interesting. It's not surprising, since this works over serial, that we need some kind of frame type here. I'm not going to cover that really at all, other than to say that it provides the sort of features that just about any other SCADA protocol would provide. There's destination and source addresses, so you can do things like multi-drop. It has some CRC detection using some pretty modern, well-vetted CRC algorithms so that we can distinguish random data corruption from false positives at the cryptographic layer. So what we're going to focus on this presentation is the cryptographic layer itself. And since they're 2 completely separate entities in this sort of 2-layer architecture, you could do things like not use the link layer at all and then pass cryptographic layer messages over some kind of message-oriented transport, whether that is UDP or a message bus or whatever. We're trying to leave that as open and flexible as possible for people to take the pieces of SSP-21 and use them in different applications. One example would be that we could retrofit DNP3, for instance, by inserting the cryptographic layer between the transport and application layers of the current DNP3 stack and have a secure DNP3. So I think that I'm hoping that people will come up with creative ways to use SSP-21 in existing systems. One of the first things that we decided when we were looking at how to build a new protocol, well, let me back up and say that I'm all too familiar with input validation bugs. We wanted to have very, very simple to encode and to encode messages. And we chose to use a sort of ASN1 light syntax to define our message formats. And the importance of that is that it makes it easy for people to generate parsers and formatters in a very automated way. So instead of hand coding parsers and formatters, we're actually automating that with the reference implementation. But we didn't want to use a scheme as complex as ASN1. So it's been a hotbed of security issues, ASN1 BER, DER over the years. So none of that cruft that people traditionally hate about ASN1 is in there. There's no embedded length fields, only fixed with integer types, no string types at all, no optional types. It's very, very simple to write a parser for this. One of the downsides is it's not self-describing, but I really have yet to see very many people that actually use the self-describing parts about ASN1, because without the context of what fields mean, it's not very useful anyway. So on the right there, you can see that's just a definition of an enumeration in the protocol. So those are the different function codes. So you should be able to guess that there are 6 functions in the cryptographic layer, 6 different message types. So here's a message definition for the first message that gets sent when what we call an initiator, which would typically be the master in a system, starts a session talking to the responder, which would normally be an outstation. So there's always, it starts with a fixed, a fixed byte request handshake begin enumeration. There's a 16-bit version number for the protocol, so that very early on you can tell if the two sides are speaking the same language. And then there's a number of enumerations that collectively define, we don't call it a cipher suite because it might not even use encryption. We call it a crypto suite specification. So this is one area where SSP-21 is already starting to differ from something like TLS, is that we don't do negotiation. The initiator tells the responder, these are the algorithms that you're going to use. And the responder can always say back, I don't support that, but we're not designing this for the World Wide Web where you have diverse components from many, many different people, and they might want to do negotiation. This is more for private automation networks where the capabilities of all your components. So we're already starting to remove some of that cruft out of TLS and keep things simple. And then at the bottom, the most complex types that we have in this sort of grammar so far are just opaque sequences or blobs of things, right? So that next item there is the ephemeral public key. Sequence 8 means that it's prefixed with an 8-bit count. So there can only be up to 255 bytes in there. And then although we're not supporting PKI yet, and I'll talk about that in a second, there's a placeholder for a sequence of sequences of those, so a certificate chain. So there are some provisions in the grammar there to limit counts and things because the objectives are that you can do all of this without any heap allocation. So we want our parsers and our message formatters to be able to operate very, very simply, not even have to malloc for real-time systems. So I know this is the session right before lunch. Now we're going to do some cryptography. Should get everybody really hungry. I know not everybody's a crypto expert or uses cryptography on a daily basis. I'm not a crypto expert. So we're going to go through just some of what these primitives are, so that when we get into some of the more heavy slides, people will know what we're talking about. I think everybody is familiar with what a hash is, right? You see hashes all the time on websites. It's just a digest that takes some input allocation and produces a tag. Most of you have also heard what a message authentication code is, or a MAC. That's a function that takes a secret key that you keep private and a message and produces a digest. So that's one of the fundamental primitives we use to authenticate messages that go back and forth. We also use a key derivation function. Key derivation functions take a salt, which can be publicly known, and some input key material, which you want to keep a secret, and they produce some output key data. Okay, so we use this for our session key derivation. And then last but not least, a Diffie-Hellman function. So a Diffie-Hellman function takes a private secret that you know and a public secret from somebody else and allows the two parties to derive a shared secret.
Do you want to talk about the noise protocol real quick?
Yeah, good point.
So we borrowed heavily from the noise protocol, which is a framework for designing security protocols.
Yep. So noise is an effort by Trevor Perrin, who works a lot with Moxie Marlinspike and the Whisper Systems guys. And noise had a ton of features and that were all really well reviewed, but we couldn't use it directly because of a number of things. Noise has this neat feature where it hides metadata. Like you don't even know the parties encrypt first before they exchange certificates. And those kind of things is like, it's great if you're a journalist in some like repressed country trying to communicate out of a Tor exit node, right? But not so applicable necessarily for ICS. So we tuned down some of those things that were more like super privacy oriented and encryption oriented, but we are reusing a lot of the same primitives and compositions. So those are the abstract crypto functions, right? I do want to mention some of the actual concrete primitives that we're using. Shouldn't be surprising that one of the options is SHA-2. We're also looking at the Blake family of hash functions because they're really fast in software. We can get latency down during the session when we're authenticating tags. Obviously, if we're using SHA, we're using HMAC SHA. We're looking at keyed Blake 2 as an option for a MAC. The KDF that we inherited from noise is HKDF, hashed HMAC-based key derivation function. You can go look at the RFC. We're also looking at having a secondary option because we want multiple options, so there's no one crypto component that can be found vulnerable and suddenly we have a useless protocol. And then for the Diffie-Hellman function, our first option there that we're implementing is curve 22519, which is it's a Diffie-Hellman scheme and a digital signature scheme that Daniel Bernstein and his team have put out. And one of the nicest things about it is it's really fast, one, and two, it's really easy to write implementations that are constant time, that don't have easy side channels. And there are a number of good implementations of that in a number of languages. Okay, so now we get into the meat of how our key agreement and things work. We have a 4-message handshake, so that's 2 back and forth round trips. In some systems, that second back and forth round trip could be optional, okay? So what happens in the first message is the initiator sends an ephemeral public key and some metadata for the cryptography seat and says, I'd like to start a session, okay? Then the responder sends back, yes, let's do this. Here's my ephemeral public key. I support all those algorithms. And then they derive some keys together, and then the second 2 messages are all about the authentication step. Noise didn't have that second authentication step. Noise would then just start transmitting, and if the message tags failed, you weren't authenticated. But for sessionless environments, we didn't want, one party on a bus, think about an RS-45 or a multi-channel radio, just to be able to blow away sessions with a single message. So we have this secondary authentication step with the second 2 messages there. So quick review of Diffie-Hellman with some graphics. 2 parties will have 2 key pairs, right? Key pair, public key, a private key. They send each other their public keys, and then each party is able to use the Diffie-Hellman function to derive a shared secret. Okay, so this is going to become important on the next slide. In our key agreement scheme, we root our trust in long-term static Diffie-Hellman keys. So that's a little different than a lot of public key protocols that might root it in, say, like an RSA key, which would be more of a public signing key for digital signature, not a Diffie-Hellman key. So that's one area where we've used some concepts from noise. So the first thing that happens is the initiator derives a ephemeral Diffie-Hellman key, and then that's denoted with this E sub I. So that's static key for the initiator, ephemeral key for the initiator, static key for the responder, and ephemeral key for the responder. And the initiator sends this first message that contains his ephemeral public key and the static public key, which might later be embedded into some certificates. In the mode where we have only pre-shared keys, where you would use the protocol like you would use PGP mail, where people sort of share their public keys out of band, that static key might not actually be in that message. And then both parties, before they do any other cryptographic operations, initialize this variable called CK that we call a chaining key. So they just hash the entire message. And this whole point of this chaining key that you're going to see in the next few steps is for handshake integrity. So we keep a running hash of everything that both sides sent for the whole message. And that's the sort of protection that's designed to protect against things like downgrade attacks to make the protocol future-proof so that man in the middle can't manipulate handshake values. So the responder receives that message, produces the same chaining key, and responds with his ephemeral public key, possibly its static key embedded in some certificates, hashes the message, the initiator receives the response and hashes the message. So at this point, both parties have exchanged their ephemeral key data, and they both should agree on the CK if somebody in the middle hasn't manipulated the messages in some way. Now, here's where things get interesting. Both parties do a key derivation, okay? So they use the chaining key, which is completely public information right at this point. Any man in the middle could see those messages that are exchanged. He uses that in the KDF as the salt. And then each side performs 3 Diffie-Hellman operations. And if you look carefully at what these Diffie-Hellman operations are doing, is they're doing, this Diffie-Hellman operation would be just like in TLS. It's between the ephemeral private and public keys. And the second 2 are permutations between the static and the public keys. So that's basically how we accomplish, how we're going to accomplish authentication with public key cryptography without using digital signatures. So we're mixing in these permutations between the static and ephemeral keys as the input into the KDF. So we concatenate these 3 Diffie-Hellman results, and that is the second argument into the KDF. And then we actually derive 2 keys from that. We derive a new chaining key value and a key that we call the authentication key that we're going to use it to authenticate in the second 2 messages of the handshake. So each side now has a chaining key and an authentication key. And the initiator sends a message that's a pure authentication message. In fact, the MAC is calculated just over the fixed pattern OX01. The other side receives it, rehashes it. We're keeping that running hash going of the conversation. And then the same thing in the other direction, except for the MAC's calculated over a new value. So at this point, both parties know that they're talking to somebody that was able to derive the correct keys. So they've authenticated with each other. Now, the last step is to derive the actual session keys. And to do that, we basically just split the chaining key. So the authentication key that we used is cryptographically independent from the chaining key, which came out of the KDF. And we split that CK using the KDF into transmit session keys and receive session keys. So you can see that these are flipped here because the 2 sides are going to use the keys, one for receive, one for transmit in the opposite direction. Okay, great. So we have a session now, right? We have session keys that we can use. So what are the limits of those session keys? Right now we have a nonce defined on the messages just to be a 16-bit value, which right out of the gate, that's going to limit you to 65,000 or so messages per session before you have to renegotiate or do something. We haven't really decided on defaults for what that might be. It could be part of what the initiator sends in the handshake message, thou shalt not use your nonce for more than these values or so forth. And then the other limit will be sort of the classical time-based timeout. We have a 32-bit field on the session messages that's milliseconds since the session began that we use as that TTL. So that limits us to sessions not lasting longer than 49 days, but I think most people are going to want to renegotiate sessions faster than every 49 days, so that's not a limit there. So here's what the actual session messages look like, once again, reusing our grammar. The auth metadata has been pulled out of the session message, so that's just a struct in here. And in fact, if these values were directly inside this definition, it would produce the same serialization. This is just so that we can define the data very explicitly that also needs to be covered by the authentication tag. So this data, the nonce, and the validity are never encrypted under any of the session suites. They're always clear text. But they always need to be covered by whatever the authentication tag happens to be, whether that's a MAC or whether that's the tag in an authenticated encryption mode. And then in the session data message, all we really have are that metadata that needs to be signed, a clear text or encrypted payload for the actual application layer protocol that we're protecting, and the authentication tag itself, which might be a MAC or it might be an AEAD tag for something like AES-GCM. So that's the basics of the protocol. That's kind of what our first version of the spec defines. It defines basically using pre-shared public keys. The next phases down the road are going to be add PKI.
UKI, as we're calling it, because we really want a much lightweight, simple, and the way that devices get authenticated in an ICS environment is very different than in an IP world.
Yeah, why don't you tell us about the intent for the reference implementation?
So this is basically it's going to be open source, a BSD license. There'll be no intellectual property associated with it. So we really want vendors to implement this in the products. And as utilities, right, we don't need to make money off of a protocol. We really want to reduce the barriers to implementation. So with a reference implementation, they can start with running code and then adapt it to their product. And the BSD3 license, and we are having Lawrence Livermore do the validation and verification of the protocol as each time we do an enhancement to it to provide like an independent analysis of it.
I think reference implementations are something we really fall down on in this industry. We pay armies of consultants many years to construct 1,000-page IEC and IEEE specs, and by the time they get to Plugfest, things are so inherently complicated that people can't talk to each other. So this is something I think that we're hoping to put out as a working prototype with production, quality code. We're taking some real efforts to make sure that the code is very sound. But I'm hoping that will enable us to accelerate our period until adoption by actually having a reference implementation.
We're also looking at doing a bug bounty as well, so to try to harden that reference implementation.
One of the greatest things about reference implementations and doing them in combination with the spec is you get to do this iteratively, right? I mean, we're already making changes to the specification because it's like you find something like, man, that's really hard to implement. It's really hard to implement. Well, we can change the spec at this point, and that's the approach that we're trying to follow. So I'm going to give you some technical highlights of what we're doing with the reference implementation. Because we are looking to deploy this in embedded products, we are using a native language, so it's a really lightweight subset of C++. It's a subset that I've used and even embedded on things like microcontrollers before. So some of the things you'd expect from embedded code, no heap allocation after initialization as a general rule. We're not using a lot of advanced C++ features like exceptions. All those things that you would normally turn off anyway if you were trying to get C++ running basically as a C without the C++ runtime library. And I think I already mentioned this, all the parsers and formatters are being generated from a model of the grammar. So we don't have a compiler that takes those message definitions, but we are modeling the messages, and I'll show you actually a screenshot here in a second, and then spitting out our parsers and grammars. And the cryptographic plugin the cryptographic backend is fully pluggable. So we're doing everything right now with libsodium, but if people have like hardware accelerators for some of the primitives that we have, you can swap all of that out very easily, or use a different library entirely. So I don't know how well people are going to be able to read that, but I think you can read this, right? I mean, this is our #1 goal with the reference implementation, is to create code that looks like the specification. I think if I point to some things on here, you'll probably be able to tell what this is. This says derive authentication key, and here are the 3 Diffie Hellman operations, and there's the KDF being called. So I mean, this is just one example, cherry-picked out of the code base to show that we're really trying to make the code look like the spec. Here's a screenshot of the DSL for the messages. So this is the same initiate handshake message modeled in SCADA, just because I happen to like that as a language for doing code generation. So you can see the message fields here defined, a human-readable name for logging and pretty printing purposes, and the function code defined. So this line is all we need to do to spit out a new message type or manipulate a message type. And it's not just for security purposes, it's also for just productivity purposes. As we change the messages and add fields, as this early version of the spec evolves, it's already beginning to save a lot of time to kind of generate a lot of this stuff. And there you can see the header file that model actually spits out. And the implementation file would probably be more interesting to folks to see what we're actually doing with the parsers and stuff to make them safe. But this message is doing basically zero-copy parsing. So when you parse things that are variable length, it'll return like a slice of that buffer, so that it doesn't even have to do copying and so forth. I've got a little bit of experience with community building from running OpenDNP3, so I know that things that developers and companies that are looking at open source look for in terms of quality. So we've already got a CI server stood up. Right now it's private to members of the group, but we're hoping to make that public. We're doing things like on every build, pulling down the code, running unit tests, running some static analysis. When the code goes open source, I'm hoping that we'll be able to use some of the more capable commercial static analysis programs like Coverity that offer free licenses and stuff for open source projects. And I'd like to also start doing some fuzzing with programs like AFL and so forth. Although I'm pretty confident that our parsers are pretty solid. So that will be available to community members as well. And this is the timeline for the things that we have coming, and I think I'll let Rich talk about this.
So this is for the next phase when we're going to be adding in the utility key infrastructure. And this just kind of shows the iterations of putting in a specification and upgrading the reference implementation. As we get into the utility key infrastructure, we're looking at some things where we could use something like a security automation orchestration platform where the messaging between the master and the proxy, if you will, would be simple, but then how utilities or how any company wants to go and actually implement the way they validate their devices can be flexible and designed as a playbook. The other thing to bring up here is as the protocol and the specification implementation get hardened, we are going to go and work with a standards body, most likely OASIS, because we have experience with them. You heard my colleague Dan talking about STIX. So STIX is being standardized by OASIS, and they do a really good job. Not a lot of the bureaucracy that there is in like IEEE, and so this will become a standard-based implementation.
And I think there's a lot of other applications besides ICS where a machine-to-machine security protocol, purpose-built for machine-to-machine communications, low bandwidth, low CPU are applicable, right? Think Internet of Things and so forth. So I think working with a standards body will help expose us to other verticals and so forth. So kind of closing on a couple other things for our next phases. I think that there's a need for things lighter weight than TLS and X509, okay? X509 certificates with RSA are multiple kilobytes. You're not going to be pushing that down a 1200 baud radio link or so forth. So, we've been looking to see, there are other standards and stuff out there, and there really aren't a lot of stuff. You would think that there were for embedded systems or near-field communications. We found one called machine-to-machine format, but it's really too X509-like. I mean, they're still using ASN1. It's still pretty heavy. They've reduced the size a fair bit, but it's still carrying a lot of baggage from X509. And we really want to stay away from that term for our embedded systems.
Yeah, another feature there is the fast revocation, sort of the implied. We'd like to get away from having to send certificate revocation lists out to all the outstations. Yeah. So the master's certificate will have a very fast expiration period and reduce how often we have to revoke those from outstations.
So we'll recommend a number of schemes that people can use to address things like revocation. And that'll be one tool in our toolbox. Yep. So one thought I've had is that for certificates we could possibly reuse our message grammar to define the certificates themselves. Our grammar and our message dialect is there's only one way to encode things. There's the canonical representation, so it's pretty good for things like certificates. So you can imagine defining a certificate envelope like this. You have some opaque certificate data, an issuer ID that might be a 64-bit value. This is the signature algorithm and then the signature. Okay. So one nice thing about 25519 is it comes with what they call an Edwards curve digital signature algorithm. So there's a companion digital signature algorithm also with that. So we can produce signatures as well. And there's so much cruft in X509 that's just not relevant to utilities. I mean, a lot of people don't even use things like domain names. I've heard a lot from manufacturers like, gosh, what are we going to do? Like X509 wants us to know the IP address of this before it's even defined and put in the device. So there are real provisioning issues with X509 because it just was not designed for these kinds of systems. So this is a chance for us to go back to the drawing board and say, well, what is the metadata that we think people need in these kind of certificates? So, just a stab, I did this just last week. I mean, you could just say, well, it's got to have an ID, right? You got to know what the entity is. You want to be able to time box the validity of certificates. We're not going to use some crazy string format like X509 has, just Unix epoch milliseconds since 1970 or something like that. A type of certificate, and that could be a bit field saying what the permissions are. Is this an intermediate signing certificate in a chain? Is it a node certificate? I'm sure that scheme will become more complicated and well-defined as we go along over this next phase. It's going to have a public key embedded in it, and the public key might have a different type, depending on, to tell people what it is. And then I think it will be important to have some support for extensions. So I know you heard Daniel Clark talk about that modbus.org was looking at embedding things like permissions into certificates so you could do role-based authorization. That's where that would come into play, because I think that would be really, really valuable, what he was talking about on Tuesday, being able to install a certificate on a device and that device basically be able to enforce things like read-only for that particular session. So I started playing with this, and then with those assumptions, 64-bit IDs, a 64-bit signature, 32-byte keys, and no extensions, we can encode that in 129 bytes with this scheme. They can get really small. I mean, you could use that for near-field communications. You can definitely do it over, existing serial networks that people don't want to in place. We can send this all kinds of places that X509 won't go. So that's pretty exciting, but we have a lot of work to define what this certificate format will be. And then actually figure out how that fits in to ease key management is a really hard problem.
So one of the things we are doing is working with our OT subject matter experts to understand the workflow for how the devices are provisioned and maintained so that we dovetail the certificate management piece into their normal workflow so this doesn't become an impact to the operations. These are, so hopefully you'll get these slides, but we have a Slack set up today. You can send me an email and we can get people added into that right away. We are going to be, Adam's setting up the GitHub to take it from Automatak and put it into an SSP-21 GitHub that'll be public. And we also have a Google Groups that we've set up too that you can send an email to, to start collaboration through there as well.
So I was going to say that while I believe we don't have the sign-off yet to publicly release anything, we are willing to bring on board vetted partners and people from this community that are interested in participating, like right now, so you can email us and become involved.
When we make it public, people will still have to ask for permission to get into these groups, but there certainly won't be any restrictions from somebody who, obviously, would be a contributor.
Yep. So if you want to see the spec or play with the reference, see where we are with the reference implementation, just email us and we can work with you. That's what we have.
Okay, do we have any questions for Rick or Adam? Yes.
Rick.
One of my questions is I've been doing vulnerability assessments on a lot of these systems for a while, and I'm starting to see a trend of FPGA-based development. How friendly are some of these codes and schemes that you're looking into as far as FPGAs go?
I had this exact discussion with Andrew, who was talking about hardware-based, getting all the code out of ring 0, and I think that the 25519, the public key stuff, would be the challenge, but he seemed to think that it was quite doable and was rather excited about it. So that would be very exciting. I mean, certainly AES, the hash algorithms, all those are in hardware. I mean, those are commodity primitives that you can buy an accelerator chip for. People have, Verilog definitions for hardware acceleration, but that's a question people that work with hardware a lot could probably answer better.
We actually have had conversations with Intel about they want to take this once it's a stable reference implementation and implement it in an Altera, because that's what company they bought.
But I think that the fact that even our certificates and things, the fact that they don't require heap allocation, that they're very, very simple, amends itself much more to hardware implementations than some other things.
And the reason why I ask is because you're building this for SCADA. You're building this for long-term communication over whatever transport you particularly like, all right? And you're trying to make it lightweight, et cetera. And I'm already looking towards DCSs. So, one of the things there, of course, is multicast broadcast. So, any potential for multicast broadcast type commands in this protocol?
Multicast is tough because then you have to have a lot of people sharing the same secrets, and that becomes a risk. We're not really designing this for multicast in that way.
Understood.
Yeah. Got a question in the back there.
Thank you very much. Great presentation, by the way, and I do want to get involved. Okay, my question for you, the Diffie-Hellman algorithm is great, easy to implement, it's fast and stuff like that, but to eliminate the man in the middle, we're having to add station to station on top of that, and we're getting a big performance impact. So what are your numbers are you seeing with this particular implementation?
We haven't tried it yet on embedded hardware. It's been mostly from things we've read in the literature of how it performs on ARM-based systems. I mean, it's, from what I've read, we're going to be, a couple order magnitudes better than RSA schemes with software implementations. But I just don't know. I mean, we're going to start prototyping this with a bump in the wire on some commodity Moxa stuff. I mean, you think like a 200 megahertz ARM starting at the end of the month. So I think producing those performance numbers and impacts will be part of the next phase. Yep.
Any other questions?
Yeah, great work, guys. On your implementation plan, are you thinking about standing up a public endpoint to represent, say, an outstation or something like that?
Yeah, Schweitzer's a vendor of ours, and so is Eaton, and they have discussed doing a proof of concept where, for example, they have a port server, their 3610, that they could do a reference implementation on, talking to a an Eaton SMP that would look like a SCADA master, and doing sort of a proof of concept implementation for a bump in the stack.
Did you actually mean like standing up a cloud service that people could talk to?
That's what I meant.
Okay, that's important stuff too. It's not something I'd considered, but I don't see why not. Like a simulator, yeah.
Like a master that talks to the protocol?
I definitely thought about putting together like protocol decoders and things like that, or writing Wireshark plugins, things that would kind of ease people in implementing this. But that's another good idea.
Oh, so it could kind of be like a test harness in the cloud.
Yeah.
That's a great suggestion.
Yeah, I had one as well about, okay, so you talked about ASN1 and that you were eliminating all of the cruft, or at least the pieces that you didn't feel were necessary or that you felt were dumb. Do you have a list of those that you could put out?
It's easier just to list the things that we're using, I think.
Yeah, probably. Just curiosity there.
Stefan Beira from GI Net Consult in Germany. Is there any chance that that can become an international standard, like an IEC standard?
I think Oasis does do international standards.
Yeah, but IEC is a bit more well known among vendors. I'm asking because you seem to have vendors in your group, but obviously they're all American-based. And
there haven't been any final decisions on what standards body to work with. So yeah, we'll definitely take your your feedback
from
about
a
that.
European perspective, we have a lot of small vendors, and we are always looking at IEC, kind of what we want to implement, and so it would be probably a good support if it would be an international
I would say that
standard.
there would have to be a compelling reason to work with standards bodies that have a lot more bureaucratic overhead, like IEEE and IEC. That would be very painful personally to me. So
originally we were just going to do this as through the IETF and just put the running code out there and see what happened, but I lost that argument.
there are pros and cons, right? Yeah.
Got one more.
So, I mean, I like what you're doing, but I also know doing like good crypto right is hard, which is why lots of the world just says, well, we'll just use TLS because people have beat on it for years and figured it all out. So I guess I have two questions. One is, it sounds like you haven't gotten performance data yet, but do you at least have a sense of code size savings, right? Here's how much your implementation takes X number K versus a TLS stack is. I mean, how much?
Well, I can put it to you this way. I mean, what is the OpenSSL code base with libcrypto and SSL is like, I think it's like 150,000 lines of code or something, and we're sitting at 4,000.
Okay. All right.
And that does not count pulling in the primitives from libsodium, but the code base is going to be very small compared to at least OpenSSL, and there's lots of specialized TLS stacks for embedded systems. I don't have the numbers in those, but I think that'd be very useful to do, is to compare code
until
size
you get
phases.
the number that matters is the performance numbers, but,
Yeah.
but that's at least some metric of, oh, how much smaller is it?
Well, it's important to manufacturers too, because no one wants to blindly, especially put something new into a system. If you can say, hey, there's only 4,000 lines of code here, you guys can have a really in-depth look at it, without,
In what you have, right?
yeah, with a small team. I think that's,
then the other question was more on the crypto. Like, you need, I'm assuming, I'm not a cryptologist. It didn't sound like you are, but it sounds like, is somebody in Lawrence, Livermore, is that the people, the mathematicians?
Yeah,
that
we
are
got a
really
guy named
tearing this
Crypto
apart?
Boy. That's his handle. Who's
Okay,
looking
but
at? He's part
you
of the
need somebody to
verification.
really, that's hard, and typically that's like peer reviewed and.
there's a difference here between, I think, between primitives and composition. Certainly we're not tackling primitives. And to a certain degree, we're not even tackling composition, because we've borrowed composition from protocols that have gotten extensive review. And then on top of that, we are bringing in third-party experts like the folks at Livermore. But that's a very, very valid concern, but those are the things that I can say to address that.
Well, actually, we have NSA represented here. We'd be happy to disclose everything to them.
That's just my concern. It's really hard to get that,
Yep.
which is why everybody just doesn't do that.
Well, that's one of the reasons why we're doing a reference implementation as well, is because it could be vetted by the community and verified that it's effective.
Yeah, really awesome presentation, and I can see you've really managed to optimize the security transport for that use case, but you're also thinking about in the future you might need more complex key management and support for certificates. And are you worried at all that the advantages you get by avoiding TLS, you might have to trade them off in the future when you bring in key management and certificates?
To an extent, yes. I mean, adding certificates adds things like a lot of pre-authentication parsing and so forth. But there's a lot of parts of TLS, for instance, that exist that really don't have to do with the PKI part that we're not using too. Like, one example is the fact that TLS has all these different modes for just authenticating the server or doing mutual authentication. And it was funny, I was talking to somebody, I can't remember who it was, earlier this week. They were talking about how a vendor had deployed a product but had misconfigured their TLS stack to only authenticate the server. So, it's things like that, all the bells and whistles, where we really only want mutual authentication and so forth, I think simplifies things. Certainly, certificate chains are not simple, and that will add overhead. Yeah.
Okay, I think this is going to be the last question.
And it may be a quick one, but I know the San Diego utilities are experimenting using quantum encryption techniques with photon. Are you looking at that at all? As
Oh,
kind
yeah,
of the next wave?
So this is probably going to be the talk next year. I'll bring Dr. Duncan Earl with me, because to get me to answer the quantum cryptography stuff, but he explains it very well. So as Adam mentioned, we have an option in there for encryption. And so the third phase, after we get the utility key infrastructure in place, is to provide a way to deliver a one-time pad, which is a quantum cryptography key that can then be used for encryption.
We're looking at an integration point so that you could distribute the quantum keys and then mix them in the KDF. And then you'd basically have a mix of classical public key, which can be broken by quantum computers, and then the symmetric stuff, which is only halved by quantum computers in effectiveness.
So we actually have
The work's are really not quantum computing capability, it's quantum encryption, which is developed by entangled photons.
You're right.
Which really isn't a computing
methodology.
Right.
Quantum
No, I was
computing
just
is
that's
5
what
years
makes
away.
it.
It's
I was just speaking to the fact that we would use the quantum key distribution mechanism to distribute the keys,
right.
and that would bolster the part of our system that would be vulnerable to quantum computing.
Got it.
Yep.
Okay, thank you.
Yep.